Alright, another draft physics video presentation. Not really in the mood, but we'll do it anyway. Like crap. Anyway, comments. There really isn't any. So this one guy has some kind of like 2-sentence paragraph, and with things like sacred geometry in here, some sort of geometry nonsense. Kind of nonsense. I don't know. Whatever. Yes, physics has geometry in it. It's part of it. It isn't all of it. It's about movement and vectors and all kinds of things. But whatever. What does this mean? What are you even getting at? No, there's no point asking these questions. Sacred geometry. Anyway. The rest of it's just this little whatever howdy stuff. Okay, fine. You can't comment right now. I don't know. Yeah, that's right. Once a video is done being live, you have to comment in the comments section. That's right. It's not live anymore. Speaking of which, Zohar guy would be somewhere around here, I believe. Did a video. It doesn't play quite right, but anyway, provide the link below. It's physics conversation magnets. I don't know exactly if it was on the subject of magnets, but certainly magnets were part of it. So hopefully we'll do some more of those the whole idea of explaining and people understanding and communicating. It's just sort of a demonstration that, in spite of the fact that you can make videos and think you spelled it out, it's not spelling other people can understand, so it fails to work, and so then you have to do it over again and over again. Somewhere in there I think there is a right way and a wrong way, but whatever. And I thought I satisfied the requirements in some of the overview videos and whatnot plain enough, I think, but maybe not. So anyway, back to Biezen. Yeah, this is, just more fun calculating things that couldn't possibly matter. So we'll try to get to some photon theory in here somewhere. I suppose something I've been thinking about, I can throw in just as a bonus, or I had a thought about, was when they speak of thin film interference and different, things like that. They often talk about a phase shift. So they'll just have this arbitrary system where, okay, the reflections, there's no phase shift. So something can reflect and there's no phase shift. But if it goes through the surface to the bottom surface and goes through that surface, that there's this phase shift here, that somehow the photon has shifted. And they always say it's like a 180 degrees out of 360, so it's a phase shift that is catastrophic to the photon. So it sort of means that you've changed the phase in the sense that you've changed the position in such a way as obviously there's no compatibility between the two phases, which you're trying to put together, and the frequency is essentially broken. Now this 180 degrees is just on the fact that, again, it's based on their destructive interference theorem, and I'd say that obviously the flaw is that any phase difference, that is, if I was to have a phase difference that made the photons double up or something, they were really close to each other. It's as good as it gets. Or a phase shift that was not quite as dramatic, it was a little closer, then further, then a little closer, and then further. Anything that breaks the photon breaks the photon. So it ended up being 180 degrees no matter what it is, because they say this is destructive interference no matter what it is, no matter how destroyed it is. A little bit destroyed, a lot destroyed is all the same thing to them. And technically it's not that much of a phase shift. The phase shift is just the fact that you have a photon that you can't put together because the phase is off. and one that you can. And so that's why it ends up being this 180 degree number, because it just seemed very arbitrary that the thing being transmitted somehow just magically has its phase changed. Phase change would be, see, another way to draw it, is that the object is delayed in time, essentially, or sped up in time. So it's not meeting. Parts of it could meet, but I mean, it's out of phase with time. And it just seemed like arbitrary. Like, why would being transmitted cause that? And the key factor is this distance here is what's causing the change in the phase. And this distance could be a lot or a little. And so this could be off a lot or a little. And the point is if it's out of phase, that is, if it's not, what's the right way to say it? I mean, if it's halfway in between this, then obviously that breaks the frequency. Okay, so but anything in between it breaks the frequency. So that's why they came up with this 180 degree automatic phase change, is because it doesn't matter how thick this is, because it's broken. Broken is broken, and it's not fixed until you get to 360. It's not fixed till you're back on phase, till you're back in alignment. So any out of alignment is a catastrophic out of alignment, and they give it just one number, as if that's what it is, a 180 degree phase shift, when it might have just been a 5 degree phase shift, and 5 degrees is just as destructive as 175 degrees, or 150, or 100. So it's just an accuracy thing where, they've created this arbitrary phase shift, and it's really not based on nothing. It's based on the fact that this takes time for light to pass through the substance, and that's what's causing the phase shift. The phase shift is a byproduct of the thickness of the substance. Now, when you get back to another reflection, then you have this double of the thickness, and this is where I think they've gotten this one wrong, because they would say, yes, there's a phase shift here of 180 degrees. Well, again, it's really not. It could be just the addition of these two broken pieces, and obviously if this is out of phase and this is out of phase because of this distance, there's not too many times that's going to work out to 180. But it would if this thickness is just right, and you only created a 90 degree phase change going down and a 90 degree phase change going back up, then you would have your 180 degrees. I mean, you would have, so not 90, it would be 120. No, it would be 150, 170. So if it was 170 degrees worth of change, then you'd be back to 320 or 360. Yeah. Sorry, the full angle. So you'd be back on phase. So the point is that, yes, in one circumstance, that's not true. There's not a phase shift here in the sense that you're back on phase. So it's really just saying when are you on phase and off phase. It's really not saying anything specific about the actual phase shift. So it's just pointing out what I would argue is that one of their incomplete bits of understanding. They're wrong. They're describing it wrong. It's just might not be a terribly important technical detail, but it is important because it interjects some idea that there's a phase shift from nowhere, instead of explaining where the phase shift comes from. All right, on to the video.
Welcome to our lecture online. Another way in which we can try to figure out what a photon looks like, what a photon actually is trying to figure out the volume of a photon. Now, that's a little tricky to do.
All right, so that's not what they really get to, though. So the important aspect is the photon really only has 3 parts to it, right? 3? I think it's 3. Let's go figure out how many variables or features or aspects that a photon actually has. And what it has is a frequency. All right, so even if you believe in waves, it's okay. This is a wave, and this is a wave, and this is a wave. And so we're saying, okay, well, we can know that we have the frequency, the distance between the waves, how long they are, right? And that's interesting. It's probably not for me. It's never really for me. This phone. Hello? I'm speaking to the phone. It's a postal service. Yes. Computer postal service. They never got back to me, but they're asking me how well they did. And they never got back to me. Yeah. Useless. Thank you. Anyway, well, at least it wasn't spam. All right. So where was I? So you have frequency, you have the wavelength, and then realize again, like their theory is that there's some coherent wave going miles long through space, with radio waves. Some wavy thing is going, for the distance of a mile. It has some coherent wave functiony shape or something. It's just nonsense. Anyway, so so all you have is frequency, all right, and then you have the thing they never talk about is length. What's the ray length, right? So ray length, never a subject of any video ever. Will they discuss what is this thing? I mean, is there 10 of them? Is there 20 of them? How long? How much of this wave continues? And that's where it gets a little tricky, because sort of the argument I'm making now, what I've discovered, is that photons really are just composite things. It's a bunch of little ejections by electrons, and and we put the photon together. The surface that the energy hits says, did enough energy hit within a confined space of, say, 2,000 atoms? Did enough energy hit that spot to trigger a response in terms of an electron's movement, and a tipping of an electron, and that's really what a photon is, how it's conveyed. So it's not much point in saying, okay, we're going to figure out what a photon is, but we're not going to talk about how many of these nodes are in the photon. I mean, it's kind of fundamental. The other thing is obviously the speed, which most people, I think, would concede is pretty much nailed, that you don't really find that there's any speed change in photons. There's only surfaces that translate the photon into another form, a similar form of the energy, but it's being transmitted through a process that takes time. Not that the photons slow down, but the process, the electrons that are conveying the energy, the momentum, they slow down. They don't go as fast as photons. So the photon progress is deterred or delayed by the fact that it has to travel through a mechanism that forces it to move electrons some distance. Just my free addition.
Because a photon is really part of an electromagnetic wave.
No, it isn't.
And it has a certain amplitude of vibration.
No, it doesn't.
A certain change in the electric field per unit of time as it.
No, so he just said it has an amplitude of vibration. Now, that can happen. You send a bunch of photons, you can change amplitude. So you want to change the amplitude of a radio signal or something else, you just send more photons. Send less, send more, send less, send more, send less, send more. So it has nothing to do with the amplitude of the individual photons. So again, they're giving a group property to the individual photons. There's group behavior. Group behavior can be wave-like. The individual function is not wave-like. And that's how simple this whole quantum mechanics argument is they just keep looking at a group function and calling that the essence of the thing. And that's not the essence of the thing.
Vibrates back and forth, but let's take a first swag at it, and then we'll do some more videos to try and zero in on this particular concept. What does it structurally look like, and how big is it? What is the amplitude, and so forth? But anyway.
So the amplitude, the polarization is all a photon can have. It can have a polarization, a width, a height. It has nothing to do. It has nothing to do with the strength of the photon. It's anything that would be associated with amplitude. Amplitude has to do with when you draw the photon as a wave function. you can say, yes, the receiver received a lot of energy. Yes, the receiver received a little energy. And you can make that look like a wave. But it has nothing to do with the amplitude of the individual photons.
Let's take this for example. Let's say we have the sun right here, which is shining brightly onto the Earth. The intensity of the sunlight when it reaches the Earth is 1,361 watts per square meter. So every square meter surface on the Earth that's facing directly perpendicular to the direction of the sunlight has an energy influx of 1,361 joules per second for every square meter surface.
Right, so it's joules per second. So again, the trick is when you say a second of time, you say this much light. That's a light traveling over one spot for a period of 1 second. So essentially it's not a square meter, it's a cubed meter. It's a cubic meter of energy.
And knowing that the wavelength of every photon is on average about 500 nanometers, we can then figure out the amount of energy per photon and then try to figure out how many photons there are in a particular beam of the sunlight. So let's imagine.
So there's lots of assumptions here, but regardless, I guess I'm not going to pick on them, although they should be picked on. Because they would change the wattage based on the frequency of the light, to do lots of things that only make sense if you have some sort of clinical, sterile, unreal circumstance, some ideal circumstance. Where each ray is the same length, where each bit of the light, the photon, isn't reconstructed photon. So if you make the ultraviolet light this long as a ray length, and then you convert it, into infrared, that you don't have to account for the fact that you have more bits to deal with, that it's going to end up being a longer ray, because you can't put the same frequency into a same size package and have the same number of nodes. So because they've just arbitrarily called them waves, they can make the wave nodes as long, the ray length is any length they want to, when length is going to be tied to how many nodes does it have and what was it made out of originally.
Imagine for a moment that light travels at 3 times 10 to the 8 meters per second. We don't have to imagine that, we know that, of course. And so we know that in 1 second of sunlight, there will be a beam that is 3 times 10 to the 8 meters long, 300,000 kilometers long. And if we make the beam 1 square...
So 300 kilometers long. No. So, I don't know. Does that make sense to you? So he's basically saying for one photon to pass in 1 second. So in 1 second of time, okay, the photon is moving so quickly that in 1 second it travels 100 and whatever he said miles in 1 second, which doesn't make sense because it's a nanometer, right? How can something being 500 nanometers in wavelength, the wavelength is 1 second? All right, let's play that again.
1 second of sunlight, there will be a beam that is 3 times 10 to the 8 meters long, 300,000.
3 times 10 to the 8 meters long. They really won't. So he's saying it doesn't make much. Okay, so what he's saying is how many 500 nanometer waves can I put into 1 meter, which would be the time that the other equation, the watts, is based on. The watts is per second, and so in 1 second, how many nanometers would fit in 1 meter? Yeah, so one second is 1 meter by watts, and so you're figuring out how many nanometers are in the 1 meter. Okay.
1,000 kilometers long, and if we make the beam 1 square meter in cross-sectional area, so that means the area right here is equal to 1 meter squared, then we have a volume of beam that is equal to 3 times 10 to the 8 cubic meters. And then the question would be
3 times 10 to the 8 cubic meters. So it's this huge, thing, this gigantic bucket, or whatever you want, a volume. It's a huge volume he's just created. So of course he's going to come up with a preposterously huge number of how many nanometer long nodes of photon would end up in that gigantic space.
how many photons would there be in that one beam? That would be 1 second worth of sunlight that will strike the Earth on an area of 1 square meter.
So it's not one beam, obviously, by any logical sense. No one would think that it's a beam of light is a meter wide, okay, by, 1,000 miles long. No one's doing that.
How many photons are there in that beam? And then how much volume, how much space does each photon have within that beam? It's kind of a way to look at it. Now, of course, that doesn't really mean that photons have volume like that, but it's kind of a concept, and hopefully that will help us figure out what exactly a photon looks like.
So that might be actually somewhat useful to figure out, what arbitrary sizes you could give photons and what the significance of those arbitrary sizes would be in terms of density. But that's not what he's going to do.
All right, so I'm kind of curious to find out what we're going to see here. Let's see, how much energy does each photon have? Let's start with that. So we know that the energy of a photon is equal to the Planck's constant times the frequency, and since we know that the speed of...
So again, we're back to the same nonsense where the equation says nothing about how long the ray is. The energy just has to do with how it reacts to an electron, and that's it. So to get a kilovolt reaction out of an electron, it takes a certain amount of photon, that minimum. And that's what everything becomes as a photon. So if it has more energy or if the ray length is longer, we don't count the extra part of the photon at all. It's as if that energy doesn't exist. But it clearly would exist. It clearly would have a consequence somewhere.
Light is equal to the frequency times the wavelength. Therefore, we can write F as c over lambda. So this can be written as hc over lambda. So that's the energy of a single photon. And so for typical sunlight with...
So again, I just argue that that's wrong-headed. To think that the wavelength or the frequency is defining the photon's nodes, it's just wrong.
An average wavelength of about 500 nanometers, that would be 6.626 times 10 to the minus 34 joules times seconds. Multiply that to the speed of light, 3 times 10 to the 8 meters per second. And then divide by the wavelength, that would be 500 times 10 to the minus 9 meters, because those are nanometers. And let's see what we get. 6 to the 6 e to the 34 minus times 3 e to the 8 divided by 500 e to the 9 minus equals, and so that gives us an energy of 3.98 times 10 to the minus 19 joules. Let's convert that to electron volts just so we know what.
Why don't you convert to watts? That would be convenient. 1 joule equals 1 watt, I think, so that would be easy.
That is, so we have 1 electron volt per 1.6 times 10 to the minus 19 joules. So divide that by 1.6 e to the 19 minus, and that gives us about 2.48 electron volts. So that is the energy of each photon on average in a beam of sunlight. So
each photon, again, by no description, they haven't distinguished, and so I would argue that as a composite, you can add up how many times you create this order, this capacity to tip an electron. And that's all you're really measuring is how often you tipped an electron. Period. It's not measuring the misses.
How many photons do we need to make up 1361 joules? Remember that the intensity is equal to 1361 joules per second.
I mean, I would argue over a lot of permutations, the misses are always going to be a consistent amount. There's going to be a certain probability about how long each photon is and all that kind of stuff. So this is just telling you some sort of average. It's not telling you really anything about what individual photons are doing. Or not much about what individual photons are doing.
And that's what a watt is, divided by a square meter. So how many photons do we need? If each photon has this much energy, how many photons do we need to make up this much energy striking the Earth for every square meter every single second? Well, all we have...
So you have this minus 19 watts, so you can sort of get the idea that it's a billionth or a trillionth or a zillionth or, of a watt. It's a very small amount for photon.
Have to do is to find the number of photons that's equal to the energy in the beam divided by the energy per photon. So in this case, that would be 1361 joules divided by the energy of a photon, which is 3.98 times 10 to the minus 19 joules per photon. And that will give us the number of photons. So 1300. Well, first of all, I'm going to go back to that number that I had. So
again, they're just measuring how many times they provided enough energy to tip an electron. That's all, to create an electron volt.
6.626 e to the 34 minus times 3 e to the 8 divided by 500 e to the 9 minus. Okay, so I don't have a round off error. So I divide that now by 3. I don't want to divide that. I want to take the inverse of that. Take the inverse of that and then multiply that times 1361. There we go. That's better. And that gives us the total number of photons of 3.42 times 10 to the 21 photons. So a beam of sunlight, 1 square meter in area, in cross-sectional area, that will strike the Earth in 1 second, that section of beam will carry that many photons. That's a lot of photons. But then...
So again, he came up with the same number he started with? No, it's a different number. So this was supposed to be the amount of light hitting 1 square meter. So he just said it the same way. What he means is a thing, this arbitrarily long volume contains this many photons.
How dense are the photons? How much space would be for each photon? So let's go ahead and try to find out the number of photons per cubic meter. So number of photons per cubic meter. We take the total number of photons, which is 3.42 times 10 to the 21 photons.
And divide it over this giant volume he created.
And we divide it by the total number of cubic meters in the beam. And that was going to be equal to, right here, the volume, 3 times 10 to the 8 cubic meters.
So 3 times 10 to the 8th is 3 billion meters, square meters, huge volume.
Divide that number by 3e to the 8. That gives us the number of photons in every cubic meter. So a cubic meter is about this big. It's a box, 1 meter by 1 meter by 1 meter. And that would contain 1.14 times 10 to the 13th photons. So every cubic meter of sunlight, when it strikes the Earth, contains about 11 trillion photons. Okay, so how much is that per cubic centimeter? Now, a cubic centimeter is a small little cube, 1 centimeter on the side. So that's about 1 centimeter cubed. How many photons would there be in one of those little...
Yeah, you just divide this number by 1 billion. So you just cut off some of your 13 and put in a 8.
Cubes like that when the sunlight arrives here on the Earth. Well, to find that, photons, I guess, per cubic meter. So we have to multiply that times the conversion factor. We want cubic centimeters at the bottom and cubic meters at the top. So 1 cubic meter is 1... See, it's 100 times 100 times 100. That's 1 million. So let's go 10 to the 6th cubic centimeters per meter. So how many photons in a cubic centimeter? Well, then we have to divide that by a million. So we get 1.14 times 10 to the 13 minus 6 would be 7 photons per cubic centimeter. So in every cubic centimeter of space, sunlight reaching us, there's 11 million photons. Wow, how much is that per cubic millimeter? Well, let's convert. So we have...
So it's just, let's convert by, so you did a centimeter, so you're just converting by 1,000, so you just take off 2 zeros. I can do that math.
Cubic millimeters at the bottom and cubic centimeters at the top. For every 1 cubic centimeter, there's 1,000 cubic millimeters because it's a 10 to 1 ratio. We have to cube that. So that means there's 1.14 times 10 to the 4th photons per cubic millimeter. 11,400 photons in a cubic millimeter. Now, a cubic millimeter is basically the size of that dot right there. There's a cubic millimeter. In sunlight, this much volume would be 11,400 photons. So you can see photons has to be fairly small, so you can fit 11,400 in them, 11,400 photons in a tiny little...
But their width, their spread, the amount of space they spread over is fairly large in the sense that it's 500 nanometers by 500 nanometers, so to speak, in terms of the fact that it can have dimension that's really big, more than 2,000 atoms. So one photon lands on a surface that's more than 2,000 atoms across. Obviously, if you squared that surface, 2,000 times 2,000, right, it's 4,000. So the 2 plus 2, the 2 times 2 thing always works out, right? 4,000 is simple. But anyway, yeah, so just pointing out, the photon might be small, the bits of a photon, but it does land on a big chunk of space.
Cubic millimeter. Wow. So let's summarize this. This is a cubic millimeter, and inside There would be 11,400 photons.
So that means that the photons, right? You could sort of understand that there's a bunch of these little bits, these nodes, these little wavicles, and that they're all in the same area. So there's 11,000 of them in this millimeter, and so based on polarization you could just say cut that in half or a quarter. So in that one little space there's a bunch of overlapping photons, essentially, you know, bits from different photons are flying through that space. Nodes.
Photons traveling at the speed of light towards us from the sun. When it gets here, every cubic millimeter of space has 11,400 photons in them. So that gives us kind of a feel for how big photons are. They're very tiny. There's a lot of them.
So again, they're not so small. The nodes are small. So again, he says they're very tiny, but they're not. Okay, the ray, the thing you have to see, the thing that has to affect something, has to land on a pretty large surface.
In a beam of sunlight. And again, that gives us a feel of what photons are. They're very small, little tiny packages. But to get a better feel for them, we now have to kind of find the bridge.
Yeah, so now to get a better feel for them, you have to understand. So he's basically saying, look, they're little clumps of energy, and there's a bunch of these bullets. Everybody's firing their bullets in the same area. It's going through the same hole, so to speak. There's a hole, and there's 1,000 people shooting bullets, and they're all shooting the bullets through the same hole. And so everybody's gun has bullets going through the hole, you know, at different phases, at different times. But at any 1 second, there's a certain number of those bullets. And then you go a little bit of time later, there's a certain number of those bullets. And a little time later, there's a certain number of those bullets. And all those bullets are going to end up in the same place on the target. And the target's going to decide what it's getting hit by bullet-wise. And whether some of the bullets didn't make it through the process, the ray pieces. And it's going to put together photons out of elements that came from different guns. Different guns fired at the same time. They sent the energy. The bullets are going to arrive at the same time on a surface, and that's going to decide the amplitude of the light energy at that moment.
Between electromagnetic radiation and photons. There is some commonality there, something that we have to tie the one to the other so we get a better understanding what photons really are. Because after all, electromagnetic radiation is created when particles vibrate back and forth.
So he says particles vibrate back and forth. No explanation of what causes them to vibrate back and forth, what tension does that, or what mechanisms could possibly do that. When again, we know to move one direction, to act. For something to move or change its direction, as Newton would say, you have to act on it with another force. Things don't just do it for free. The pendulum doesn't swing for free. It swings because there's gravity pushing it down from, you know. And so you have to apply a force, and they don't have any force in this. They don't understand that photons are themselves force, and they're force at a frequency. And that's the only difference. They're just magnetism or electricity. The virtual photons of quantum mechanics, they're the same virtual photons, and these happen to be at a frequency. And when they're at a frequency, they can do things they can't do when they're not at a frequency. And that's it. You don't need all of this mystery. Photons are a force. Just like your magnetic and your electric field, they are the field. They are an element of the field. The field is the photons. Photons are part of the field. And there's other stuff in the field that isn't at a frequency. And that stuff doesn't do this little electron trick. And therefore we don't consider it a real thing. But we feel it as gravity. And we see it as movement of pressure through wires. And we see it in magnets being pushed away or towards each other.
Change in the electric field, and that change in the electric field emanates through space. But yet, it's then broken up into little chunks of photons, very tiny, we're 11,400.
Right, so he's just saying, hey, look, I'm going to tell you two different stories. It's Goldilocks or it's Hansel and Gretel. I mean, they're just cramming the two fairy tales together. And one of them might have more truth value than the other. But it's just wrong to sit there and play this duality game like it's the same thing. Those are fundamentally different things. This waving, vibrating, fieldy thing versus this quantized nodes of energy thing. And you can't make the two stories the same story. It's just, you're wrong automatically. Pick one, okay, and defend it. And I think the only one that can be rationally defended is the quantization, the idea that it's a particle. It's a bit of momentum traveling through space very quickly. And that's what all the other forces are doing. Gravity's moving the same speed, magnetism moves the same speed, and electricity in a perfect conductor moves the same speed. So it's the same stuff.
It could fit into a single cubic millimeter. We'll explore to see if that changes for different kinds of electromagnetic radiation, for radio waves, for example, which have much bigger wavelengths, and for tiny little micro X-rays and gamma rays. Is it different for those kind of photons? And so,
no, would be the simple answer. It's no different except, oh yeah, they're really far apart. That's the difference. The bullet's fired very slowly.
we have a feel of how big they are depending upon what their wavelengths are. So we'll get to that, but slowly but surely we're unlocking the secret of what a photon is.
So he's saying he unlocked some secret by, again, proposing an answer that's just mush. It's dualistic mush, where he says it's left, it's right, it's up, it's also down. It's incoherent, it's incomplete, it's overtly wrong, and yet it's sold as we understand. No, you don't understand.
So still interested? Stay tuned. We got some more stuff coming up.
Yes, well, whatever. Alright, so we'll call that a video, I guess. Sorry. Till the next time and such. And so forth and whatnot. Yeah, I'll probably make a Google sucks video on this channel next couple of days. Just because, you know, YouTube is attempting to annihilate my Inmendum channel. You know, flagging videos that are 6 or 7 years old, that kind of nonsense. Yeah, I should at least do my minimum protest, which doesn't matter because nobody pays any attention. Google's evil as fuck. It shouldn't be allowed to control the internet, and it does. It shouldn't be allowed to control Android, and it does. It's an evil corporation that doesn't give a fuck about our freedom. It doesn't respect our Constitution at all. It's just about money. It's a fucking marketing company. It's worse than Microsoft. And it should be despised and destroyed. Yes. It's evil. And evil should be fought. Yes. It's a good idea. So that's hate speech. Can't say that. This video will probably get flagged. Because that's hate speech. To be against something is to be evil. If you're against evil, you're evil. Yeah. I mean, you know, it's just the ironies of what lessons people learned from the Nazis is hilarious. Because apparently they just are basically saying, well, as long as we're the Nazis, it's okay. Because they're just as bad. The victims are the perpetrators, you know. Anyway, till next time. And such.